Today I'm going to continue with our discussion of carboxylic acid derivatives. This time we're going to look at reactions of carboxylic acid derivatives. The primary mechanism, this is most of the reactions in this chapter, is one called nucleophilic acyl substitution. This usually involves interconversion of acid derivatives into other acid derivatives. The way that this works is the nucleophile adds to the carbonyl, forming a tetrahedral intermediate. The leaving group is eliminated, which regenerates the carbonyl. This is also called acyl transfer. Okay, and the way this works, this is the pattern for most of the reactions in this chapter. Okay, unlike aldehydes and ketones where the nucleophile attacks and oxygen gets protonated, in this case, we go through this tetrahedral intermediate. Oxygen pushes down and it kicks out the leaving group. Okay, so we restore the carbonyl, but we have a different group present. This is the order of reactivity of carboxylic acid derivatives. And this correlates with the quality of the leaving group. Chloride's a very good leaving group. Carboxylate's a fairly good leaving group. Alkoxide is not so good. And then the amide group, NH2 is also called the amide group, is not such a good leaving group. Okay, but this is the order of the reaction, of reactivity. Most of the reactions in this chapter will involve conversion of derivatives into other derivatives. We'll see a little bit later on that we can convert either carboxylates or carboxylic acids into acid chlorides, but other than that, reactivity is all downhill. So we can readily convert a more reactive derivative into a less reactive derivative, but not the other way around. Okay, so acid chlorides can be converted into anhydrides. Okay, anhydrides are just below acid chlorides. And this follows the same pattern. The nucleophile attacks. Leaving group is eliminated, and then we have a proton transfer, and our product is an anhydride. Acid chlorides can be converted into esters. This time the nucleophile is an alcohol. The alcohol attacks, and again follows the same pattern. Chloride is eliminated. We restore the carbonyl group, and then we have a proton transfer. In practice, you'll have a base present, something like pyridine or triethylamine, in order to neutralize the HCl that's produced. In the lab, we used a carboxylic acid and an alcohol, and you may recall we had to reflux it for a very long time. We had to use an excess of carboxylic acid because the reaction was reversible. Okay, because the acid chloride is so much more reactive than the carboxylic acid, we can do this actually with stoichiometric amounts of acid chloride and alcohol. It takes place under milder conditions. It occurs more rapidly. We get good yields. If the nucleophile is ammonia or an amine, we can convert an acid chloride into an amide. In our chapter on amines, we talked about how amines were basic. So one way of accomplishing this is to use two equivalents of the corresponding amine. Okay, we could also use one equivalent, and then we could use another base, something like pyridine or triethylamine. Okay, so ammonia would yield a primary amide. Primary amine yields a secondary amide, and a secondary amine yields a tertiary amide. Okay, you cannot make an amide from a tertiary amine. Okay, you have to have at least one hydrogen on the nitrogen. Okay, just below acid chlorides, we have anhydrides. Anhydrides can be converted into esters, again, very readily, more readily than using carboxylic acids. The mechanism is the same, just a different leaving group, in this case a carboxylate. The carboxylate then removes this proton, and we get an ester, and our byproduct is a carboxylic acid. Right, we can convert anhydrides to amides. Again, very similar mechanism. The amine acts as a nucleophile. The carboxylate then is the leaving group, which removes a proton, and as before, our byproduct is a carboxylic acid. Esters are more reactive than amides, and so it is possible to convert an ester to an amide, although this reaction is slow. It requires prolonged heating. It often requires an excess of ammonia or primary amine. Okay, so it does require a primary amine or ammonia. It is in equilibrium. Okay, although methoxide is not a good leaving group, this occurs because elimination of methoxide in this case and formation of the carbonyl turns out to be exothermic. Okay, here's the energy diagram. The first step, formation of the tetrahedral intermediate, is endothermic, and it's a slow step. It has the highest activation energy. But the elimination of methoxide and proton transfer are both exothermic, and so this is thermodynamically favorable, even though we don't have a good leaving group. Okay, we can also do transesterification. That is, we can convert one ester into a different ester, for example, an ethyl ester into a methyl ester. This does require a large excess of the preferred alcohol. In this case, it would be a large excess of methanol. Here's the mechanism. Under acid catalyst conditions, oxygen gets protonated, the alcohol attacks the carbonyl, we have a proton transfer, another protonation, elimination of the original alcohol, and then another proton transfer. Hydrolysis is splitting with water, and in the case of acid chlorides and anhydrides, this occurs very readily. Hydrolysis occurs quickly, even in moist air with no acid or base catalyst present. For example, oxalyl chloride or acetyl or ethanoyl chloride, those are both liquids. All you do is, if you open up the bottle, you see what looks like smoke coming out. And what this is, it's an aerosol of hydrochloric acid. The acid chloride is reacting with water vapor in the air. Okay, so this means that the reagent bottles need to be tightly closed. They have to be protected from moisture. Esters, okay, we have acid chlorides and anhydrides and esters. Esters can be hydrolyzed under acidic or basic conditions. Under basic conditions, this is called saponification, which originally meant soap making, but today it refers to the basic hydrolysis of any ester. Okay, this is, again, a nucleophilic acyl substitution reaction. Hydroxide is our nucleophile. It comes in, alkoxide is eliminated, which immediately produces a proton transfer. So under basic conditions, we'll get a carboxylate and we'll get an alcohol. Okay, here we have an acid-base reaction. Spontaneous direction of an acid-base reaction is from stronger carboxylic acid to weaker, which is the alcohol. Okay, as I mentioned, saponification means soap making. If we start with a fat or oil, this is a triglyceride or triacyl glycerol, has 3 ester groups, and heating with excess sodium hydroxide causes these esters groups to break down. We'll get this glycerol, 1,2,3-propane triol. Then we'll get a mixture of sodium fatty acids salts, which are collectively known as soap. Amides can be hydrolyzed under acidic or basic conditions. And again, the byproduct is either a carboxylate or carboxylic acid, depending on whether it's in base or acid. Okay, you may recall from our amines chapter that amines are basic. Okay, so under basic conditions, we'll get the amine. Under acidic conditions, the amine will pick up a proton, and so we'll get the amine salt. Okay, here's the mechanism. Again, this looks just like the ester hydrolysis. NH2 minus is a leaving group, which immediately removes this proton to give a carboxylate and ammonia. Amides can be hydrolyzed under acidic conditions. First step is protonation of the carbonyl oxygen. And this time, rather than hydroxide, it's water that attacks. We have a proton transfer. We have another proton transfer. In this case, nitrogen picks up an H. Ammonia is eliminated, and ammonia removes this proton from the carbonyl oxygen. Nitriles are considered a carboxylic acid derivative because they can be hydrolyzed to carboxylates or carboxylic acids under basic or acidic conditions. The intermediate in the hydrolysis is actually a primary amide. Okay, I'm going to go ahead and stop here.